Good morning, everyone, and welcome to our CPAESS Discovery Seminar Series. I'm Cindy Briere. I'm the SPS CPAESS Deputy Director. This position has afforded me the pleasure of working with all our wonderful science staff, as well as our postdoctoral fellows, like our guest today, Peijin Zhang. I'm delighted to have you attend this seminar series. Our scientists do everything from explore the oceans, fly into hurricanes, study heliophysics, as well as unravel the mysteries of the Arctic. And we want the public, NCAR, UCAR, and our colleagues at universities and agencies across the globe to experience the science that is being done by our scientists. Just to orientate you for today, we are going to use Slido for you to post questions. Please continue posting them during the talk and we will address them at the end of the talk. You will be able to find access in the tab at the top left of your screen now. Today, it is my sincere pleasure to introduce to you our speaker, Dr. Peijin Zhang. Peijin is a NASA Jack Eddy Postdoctoral Fellow, and he is hosted by the Center for Solar-Terrestrial Research at the New Jersey Institute of Technology. His research is focused on solar radio astronomy, weather, space weather, and the physical processes in the solar coronal and the heliosphere. He specializes in low-frequency radio imaging using facilities as the Owens Valley Radio Observatory long-wave array and LOFAR, with a particular experience in data processing and imaging, as well as solar radio burst analogies. Today, Peijin Zhang will speak on decoding solar eruptions in corona structure with radio imaging spectroscopy and modeling. With that, Peijin, the floor is yours. Over to you.
Thank you very much, Cindy, for introducing. So today we'll be talking about decoding solar eruptions and coronal structure with radio imaging spectroscopy and modeling. So to start with, first a little bit about myself. So I am, as introduced, the NASA Jack Eddy Postdoctoral Fellow, starting from 2020, end of 2023, so starting of 2024. And I'm a solar physicist, and I'm now the project scientist of Owens Valley solar arrays, the low frequency array, OVRO-LWA solar division. It's a very amazing instrument. A lot of low frequency antennas come together, forming a very strong radio telescope looking to the sky as well as the sun. I'm also a traveler. I was born in China and live in China for 25 years, and then I go to Europe. I live in Europe for 2 and something years. I lived in Bulgaria, Finland, and Netherlands and Ireland. I enjoy this a lot of places. I traveled almost many countries in Europe. It's a very nice place to stay and live and travel. And now I come to US for almost 2 years. I live in New Jersey, but I've been to quite a few places in US already. And I plan to explore much more afterwards. So I am a certified drone pilot. I like to fly my drone and take drone videos with as a recreational purpose. This is what I took in Owens Valley, the observatory. And on the right, this is a big radio telescope. It's 40-meter diameter, looking to the sky. And that's where in the back you can already see the OVRO-LWA antennas. It's much smaller. but there are 300 or something of them. It's amazing place. I would suggest everyone to just pay a visit. So yeah, back to the topic. So today will be about solar eruptions and coronal structures. And what is solar eruption and why does it happen? So from the white light or just what we see from the ground with a dimmer, we can see the white light sun just like this. Some of the times we can see some sunspots like this, but most of the time it's just very boring white disk, and it doesn't look like very active. But when we're looking into the corona or into the solar atmosphere, it is much more active, and just because it's magnetized, and so the solar atmosphere itself is a combination of hot plasma and very complex magnetic field. So it is a magnetic field that makes the sun very special and very active. And that is basically the reason why we want to study it, because it's so active and unpredictable. But the unpredictable part can cause a lot of, let's say, damages. So about solar activity and its impact on Earth, very intense activities like flares or coronal mass ejections. So we always refer to CMEs. So flares and CMEs are two most intense solar activities, and that is our very object to study in solar physics. So when that happens, there are three stages of impact for us, like when the eruption or the strong activity happens. First would be the electromagnetic waves. That will include white light and X-ray and radio that travels at speed of light. So it arrives right after 8 minutes of what happens on the surface of the sun. And the second wave would be the energetic particles. So this process, it will accelerate particles. Those energetic particles accelerated near the sun will travel all the way from the sun to near Earth's region, and some of them will most of it cannot penetrate Earth's atmosphere because of the magnetosphere. But the energetic particles trapped by the Earth's magnetic field and injected into North Pole and the South Pole will turn out to be our very beautiful, magnificent aurora. So not always damaged, but sometimes beautiful. And those energy particles can be major harm for our space exploration programs when we are trying to go out and see the vast universe. The energy particles could be one of the damage we want to avoid. And the third wave would be the mass, or the like coronal mass ejection, the mass part, and the things that's thrown out from the sun, and the plasma, and combined with the magnetic field, it will travel at speed of about 1,000 or a few thousand kilometers per second. Per second, it's not per hour. A few kilometers per second, and arrive Earth in a few days. So this will cause. This is the most impactful way for the solar eruptions, that they can cause damage to power grid and railways. So yeah, we want to avoid that as well. So that's why we want to study the solar eruptions, to get a handle of how that happens. It's nothing different from weather prediction. It's just space weather prediction. So, but how we study it is by observation and modeling. Observation is just to see it, and modeling is similar to weather prediction. We build up the model how this plasma and magnetic field evolve, and based on some physics rules to evolve forward, and combining with the observation to predict whether it will retrace or not, or how intense it is. But this problem is pretty complex because it covers a lot of scales. From the starting of this event, near the solar surface will be about very small scale, about below 0.01 solar radii, and the structures could be much smaller, like tens of kilometers. But when it evolves and pushed out and leaving the sun and pushing out into heliosphere into near the sun region, it can grow up to a few solar radii, and so it cross a few length scales, and that makes it hard to model and predict. So the way we're predicting it is to combine observation model and state of art or a very advanced model is the predictive science CME model. The input is the magnetogram at the solar surface, and the output would be the density, magnetic field, temperature, velocity in the range of 1 solar radii to 1 AU or 200 solar radii. That's using a very small fraction of observation to predict a vast amount of space. Considering you use one city of observation of weather to predict the whole nations, that seems like a really challenging work. So that's why we want to have more of other type of observation to build up our knowledge or prior to fit up to the model to make it more knowledgeable for higher places. So we have a lot of methods to observe the sun. That's in wavelengths or frequency. So in radio regime is this. So in here we have this different color bar. The blue part is what we call atmospheric window. That's what we can see from the ground. So the black part we can only see from space. So from the ground we can see a wide range of radio spectrum and a very narrow range of visible light. It's from a few like 300 nanometer to 700 nanometers. That's what we can see with our eyes, and many optical telescope operate in that near that frequency range or wavelength range. And yeah, in radio regime we usually refer them to frequencies. So below 100 or 200 we refer to as low frequency radio imaging, and with low frequency. So this is a cool figure concluding a lot of wavelengths or frequencies of radio imaging from very high frequency, like 20, I don't know if you can see clearly, 25.8 gigahertz to about 25 megahertz across three from gigahertz to megahertz, three scale of magnitude. And yeah, from lower frequency you can see outer and outer part, and that's what we really want, because when the solar eruption evolve out and leaving the sun, and that's where we want to predict, and we don't have much of observation. And why we want to do radio observation, and especially low frequency radio observation. here is a very nice figure from Dale Gary's lecture, and it outlines the relation between distance from the solar surface and the frequency or wavelength. So lower the frequency, the more far away from the sun you are pretty much seeing. So the what we call middle corona, which is very critical for us to learn how this eruption evolved outward, is in the range of 0.1 solar radii to 0.2 or 3 solar radii. This range is corresponding to the this range is corresponding to the frequency range of about 20 to 100 megahertz, which is the low frequency range. That's why we're very excited or caring about this range. So a little bit about how we do this, the solar radio observation, back to radio observation with single antenna or beamforming antennas, and we can get a spectrum. The y-axis is frequency, x-axis is time. So every time we got the intensity of the sun or the object at all frequencies. Each frequency we get a flux density, and combined together that's a dynamic spectrum. So this basically tells us at what frequency, at what time the sun is shining. It treats the sun as a point source, so it doesn't know where the source comes from. So to know where the source comes from, you need imaging. For that you need many antennas, at least 3 antennas to get a spatial idea. But with the more antenna you have, the better imaging quality you have. So many antennas, you can get a very high quality solar image like this. So how exactly is this done? So the boring math part, it's yeah, okay, I'll go really quick through this, but yeah, it's very basic fundamental ideas. So let's say if you have 2 antennas, and so in a given direction, so let's say this direction, there is a very bright radio source like the sun, giving solar radio bursts. If you do cross correlation of the signal between these 2 antennas, you end up getting the expression of f equals this integral with time, the cross correlation, and the output of that will be 2 pi times the distance and L over lambda, and that is related to the spatial. So in that way, you can get a spatial idea. That's how you convert the signals into a way that you can understand where is this strong radio source come from. So assume we have infinite baselines as continuous D. So previous we have only 2 antennas, but now if we consider we have so many antennas aligning on this line, we will have a continuous f, and by multiply this expression with u and integral in u, and you will get a intensity distribution. And this expression looks familiar with, which is Fourier transform. So Fourier transform, the cross correlation between 2 antennas, you will get a intensity distribution. This intensity distribution is what we want. So putting this in 2D, you get a radio image. And that is basically the fundamental idea of how we get radio image from a few antennas. So it's basically first to do cross correlation between every 2 antennas, and that builds the sampling in spatial frequency space, and then do Fourier transform, and that gives us dirty image because we don't have full sampling of the whole UV space. And the image we get is the image. The Fourier transform of the sampling gives us a dirty beam, but what we observe is the dirty beam convolved with real observation. This is what we do direct Fourier transform of our observed UV sampling to image domain. So from this, we need to deconvolve the dirty beam from the dirty image to get a clean image. That's what we get in the end. So, but this step, the deconvolution step, is very computationally intensive, and that's why radio image is just a very tough game of computational power. So about instrument, so Owens Valley Solar Array currently operates two instruments. First, it's the one I'm really focusing about is OVRO-LWA, it's Owens Valley Radio Observatory Long Wavelength Array. So during the day or during regular observation, it has two observing modes for imaging, which is slow visibility. It gives 10 seconds time resolution. It uses a whole array of 352 antennas, and hourly it will produce about 2 terabytes of data. And fast visibility is it separates time in 0.1 seconds, but it uses only 48 antennas. So it's a subset of antennas, and it a much higher time resolution, but worse imaging quality. It's always a trade-off because we cannot have everything, and hourly will create about 1 terabyte of data. So for this data, we need to do real-time processing to create images like this. So, and there's another mode is creating dynamic spectrum, but it's not very intense on the data rate. And so these images and the dynamic spectrum, it will be the major thing we're dealing with to using our very cool science cases. And we have another instrument. It's called EOFSA. It's a precursor of phaser. It has 13 antennas and recently upgraded to 15 antennas. It can do imaging in the frequency range of 1 gigahertz to 18 gigahertz. This is much higher frequency. It sees closer to the sun. The science cases included like spectrum imaging of the flare, very closer to the sun, like from solar surface to about 0.1 solar radii. It did some very cool science cases. And and that's about the instruments. Why we're studying the solar radio emission. For this case, it's so solar radio emission, we can categorize them into 2 categories. So static emission and dynamic emission. Static, it's relatively static. I say this because in optical, it varies like in a fraction of percent. And usually, even when there is a sunspot, it's the total flux of white light won't be much dimmer, or even when there is white light flare, it won't be, the total flux will be just a few percent brighter than the white light. So from day to day, when you look at the sun, it will be equally bright, and it just outputs very stable white light. But in radio, it's just much more variable. So the static will be varying in like 20% scale, and from slightly darker to slightly brighter, and darker, brighter again. So that's because of the background plasma condition, the temperature, the magnetic field changing, and that causes this background changing. And the dynamic emission, so the radio burst, when that happens, it can be tens of millions of times brighter than the quark sun. So it's very dynamic, and the emission mechanism can be plasma emission, gyro synchrotron, or electron cyclotron maser emission. It's a good tool to diagnose the energetic particles, and it's good to diagnose the coronal condition like the plasma and magnetic fields. So the solar radio burst, this subject has been studied for half a decade. So from World War II, like the first discovered type of the radio burst is type 1 because it's just so bright. So we categorize the radio bursts into this type 1, type 2, type 3, type 4. You probably already heard of it, but it's named in the sequence of discovered. The brighter it would be easier to discover, and type 3 is also bright, but it's just too short in time. If you don't have time resolution, you will miss it. And type 4 is faint, and but it stays for a long time. You need to have a great sensitivity to observe it. And S-burst is just recent discovered burst. It stays a very short time. The emission mechanism is not well known, and it's one of the science cases I want to look into because it's very unknown. And so yeah, we have a lot of challenges to just get a handle of how this radio burst is related to what we see and what we will eventually feel after the solar activity erupts or influence the Earth. So. And but at the beginning, I just mentioned how we study it is with modeling. So how can we connect this radio observation with modeling? So currently it's not so well connected. So the modeling is very deeply attached with the photosphere observation. It's not very good related to radio observation. That's because the radio observation itself is very complex, and it's not very easy to validate the model with radio observations. So here's an example. So from the input map of something like this, so the magnetogram, the model can predict the solar atmosphere, and with solar atmosphere conditions like temperature or magnetic field, you can calculate an image of UV image and compare with the real observations. It's very easy to validate, but such things are really hard to do for radio. And so what we do is we initialize some sort of case study. So for this type 2 radio burst, previously there's an idea of the type 2 is initialized. It's coming from the shock front, compressing. So the shock front compressing the quasi-perpendicular magnetic field and creating radio emission. And from this case, it's very interesting. At the starting of this event, the sources are aligned along the radio direction, and at a later time, it's aligned in perpendicular to the radio direction. And from the modeling, in credit to Wei Hao in Michigan University that's doing the simulation, we can see that at the beginning. So this this volume is indicating where the surface is indicating where the shock front is, and the color indicating the quasi-perpendicular angle. So how good it satisfies quasi-perpendicular condition. At the beginning, it's over the surface, so and it's pretty straightforward. So it's the source can be aligned in this direction because of the shape, but right after it's evolving outward, the condition doesn't satisfy, and after it's evolving out, the backside is satisfying this condition, but this region is more likely in a vertical manner. So it satisfies this observation of radio pretty well, and that's what we are confident to say that one of the signs that we can say. So at least this can be used as the validation of the model, and future we can push this more and more forward to put radio imaging into not validation but data-driven. So to provide more physical values from our radio observation to put into the simulation to be the driver parameters for simulations. That's a long-term goal. So okay. Another very cool project is millisecond cadence solar imaging. It has never been done, and we are planning to do this with OVRO-LWA. The science case for S-burst it's never been done with interferometric imaging in millisecond timescale, because just millisecond timescale imaging is very challenging to do, and there's petabytes of data flow if you're considering doing this imaging. So the plan is we set up the trigger, and there's a voltage buffer already attached to this radio telescope. And we set up a trigger. When the trigger is pulled down, and we just lock up all of the data into some separated area and do post-processing. And that will take huge amount of computation power and storage. For sure, we cannot do it in real time, but the triggering idea gives us an flexibility of getting much higher time resolution, frequency resolution, instead of doing real-time sync. Real-time sync can only give us like 10-second, 20-second time resolution, but with this we can get millisecond time resolution and kilohertz per channel frequency resolution. We can look into much detail, but yeah, that's a lot of work to do before it's getting done. So another cool thing we're doing is actually it's currently running campaign about is looking not only at the sun but beyond the sun. So over LWA, it's 352 antennas. The amazing part about this instrument is 352 antennas are separately connected and doing cross correlation between every two of them. The good part about this is that it's full sky, so you can zoom into any small part of in the full sky view at any time. So for sure, we're looking at the sun itself. All the radio bursts can be seen. So this is an example of a regular day of full sky image at 73 megahertz. So if you can guess what this is, so yeah, this is a sun. And this is the Milky Way, and a few bright radio sources. So this cannot be done by optical, right? So you cannot imagine you can see the sun at the same time you see the Milky Way. That would be too much to ask. But in radio, actually you can do that, because radio sources are much brighter in lower frequencies. So you can see the sun at the same time see all of the other radio sources. That gives us the capability of doing something else, which is to look at the radio sources in the background. And when this line of sight is crossing the solar atmosphere or solar wind, it's the solar wind and solar atmosphere plasma turbulence got into this. It's like you seeing something far away, but through a boiling water in front of you, and it will get distorted by that. And from that, we can know that there's a boiling water. And similar idea is we see through the solar atmosphere, and when this source is moving around, or it becomes fainter, or it becomes larger, or it jumps, we know that something's happening in between us, in between the observer and the source. So yeah, that's what we initialize this very cool project. So every year around June 14th, also now, right now, it's happening. Right now, the Taurus or Crab Nebula is very close to the sun right now. So we can see the sun and Crab Nebula at the same time. And for sure, the line of sight will cross the solar atmosphere or corona or inner heliosphere. It will be influenced by it and showing some very interesting things. So what's the motivation behind this project is, so first, we want to know that how the plasma and magnetic field behaves between 1 point something solar radii. So you can already see this is 1 solar radii. This is about 3 solar radii. It's already very faint. They can hardly see. But in far away, it's harder to see. So we want to have some sort of a method to measure how the plasma behaves. That's one of the motivation. A second motivation is even for the solar radio bursts like this, we see everything through the solar atmosphere, or we see everything through the corona and plus the inner heliosphere. So we also want to know how this plasmas between us and the observed radio burst can modify how it looks. So that's two motivations behind it. We want to get an idea of how this propagation effect affect our study. So there are previous some observation or simulation work that set up this framework of simulations. So you can calculate actually what we are expecting to see because of the anisotropic corona. So anisotropic corona is it sounds scary, but it's really what we see when we are looking at the eclipse image, like this beautiful eclipse image. We zoom in a lot, we can see some fibric structures. These fibrous structures are representing the anisotropic plasma density fluctuations near the sun. So you can see it's in this direction, it's in this direction. So away from the sun, it's always in radial direction. And we want to know how much it's anisotropic. So and there's a parameter to measure it. It's alpha. I won't get into this complex equation. So it's alpha actually describes the ratio between the amplitude of density fluctuation in this direction versus this direction. So imagine we're a person trying to, like, imagine we are a person. We are a photon trying to walk in this way. It will be easier than this way, because in this way there will be bumpy road. In this way you can just straightly walk. So that's what that's what it actually happens. So the photon will be scattered in this way a lot than this way. So that's what we're basically expecting to see, that the source, for example, at this frequency, 73 megahertz, when Crab is close to the sun, we're expecting it to see it's scattered in this way a lot, but not in this way a lot. So by measure this, we can infer by how much the anisotropic ratio is. So that's what have been done. And for so many measurements in so many frequencies, the theta orientation angle theta here, it's very close to zero. It means this direction is pretty much very well aligned in real direction, which is expected. So because you see when it's away from the sun, the anisotropic direction is always towards the sun. So that's what we're expecting to see. But there's something that we get from this work that more than previous is the changing anisotropic parameters. So yeah, because previously we don't have much way of measuring the anisotropic ratio. So this ratio, this alpha, it's pretty hard to measure in any ways. So this line of sight angular broadening way of measuring the anisotropic ratio provides a pretty valid or robust way to measure. So previously we have a constant number of alpha. It gives us this curve. And now we measure this, so it's pretty large deviation from what we're expecting. Another interesting finding is when the source is really close to the sun, it doesn't follow the Gaussian angular broadening. It's broadening not in perpendicular direction. Again, it's broadening in the tangential direction. So it follows this arc. So it follows this arc. This arc is first time we see this behavior. Pretty excited about it. And also we can measure the total flux density. It can be used to estimate the absorption factor to combine with the scattering to infer the plasma parameters. And another very interesting thing we find is that so remember we find the sources in arc shape because of the tangential direction angular broadening, and the angular distribution of the flux follows a way that the deep or dark part of the radio imaging distribution part matches pretty well with the bright part of the white light. That means whenever there's high density in the plasma, there's low brightness in radio. So that's pretty straightforward when we're thinking about this. So when you have large volume of density in front of us at this location, it will be less radio wave coming toward us. So there will be weaker radio wave in that particular direction. So this opens a new window for us to diagnose the density distribution inside the corona, because it's irrelevant to other. It's a standalone method. It gives us a very standalone measure opportunity for the plasma density inside corona. And yeah, the conjunction is happening now. So if you have other instruments that's interested in doing that, please point at the sun. And also the Taros, it's at this location. It's not far away from the sun yet. And it follows a track, something like this. It goes from here to here. So in about 2 or 3 days, it will be at here and gradually goes away. So I'm waiting for an event not yet happened. So whenever a CME or coronal mass ejection, it's going into this direction, hitting the line of sight direction of this, it will be really interesting that when we see the line of sight, it's encountered with CME. That would be so cool. So takeaway messages for this talk. Just 3 points. Solar observation can provide very unique view into the coronal activities, including the coronal structure, quiet structure, and the coronal mass ejection, the eruptive activities. And for radio observations, there will be a huge amount of data. It's 3 terabytes per hour just for imaging. And that requires a well-built real-time processing pipeline, which is what we're working on right now. And also the third is what we recently find out is looking to the bright source through the radio, through the corona, or through the solar wind. It can help us understanding the corona structure and its the activities like coronal mass ejection activities. I really want to see whether how it react to the coronal mass ejection when this coronal mass ejection passing the line of sight of Taurus. Hopefully in the next two or 3 days, there will be a CME heading into that direction. But yeah. Okay, that'll be all. Thank you.
Thank you very much, Peijin, for that fascinating talk that you have provided us.
Yeah.
We really appreciate your time to do the seminar for us. We are now in our Q&A session, and as a reminder, if you look on the website, you would see in the upper right-hand corner, you should see a link to the question and answer session, or the question center section. While people are filling in questions, and we will get to those in a second, I would like to invite you to check out our website at cpaess.ucar.edu for upcoming seminars. Our next seminar is scheduled for July 23rd at 11 o'clock Mountain Time, and that would be given by Dr. Anne-Christine Zinken. She is a program specialist with our NOAA Global Ocean Monitoring and Observing Programs, GOMO, and she will be speaking of co-designing the current and observing systems. So with that, let's switch over to our questions.
Looks like we have a question from Catherine. If you could choose anything, what would you like to have implemented or access to that would improve modeling further?
So to improve modeling, I will say the capability of inferring physics parameters from our radio observation would be the key obstacle to prevent us from putting the radio observation into modeling. So I would say propagation effect. That so when we see a radio emission or radio burst, it's not exactly at what location it is, and it's not what as bright as this is, because for that radio burst to get into our observation, it will be suffered from refraction and scattering. So to explain that, to infer that, to have the knowledge of how refraction or scattering works, we will have a good understanding of how this this radio wave is originally it is, and once we have how bright, how fast it moves and the flux and the spectral pattern, then we can infer a lot of things very precisely, like magnetic field, like density, like energetic particles. Then we can put those physics parameters into modeling. So modeling right now is data poor. It's using just the photosphere observations or magnetogram. It's using one layer to infer like a big volume from 1 solar radii to 200 solar radii, just using one surface. That's because it's data poor, but there's no reliable way to infer physical parameters from radio observation, and that's why it's not very good link between radio observation and modeling. But yeah, it will be massively improved if we can resolve the issue of propagation effect. But it's a very good question. Thank you.
Thank you. And then our next question is from Mohammed Nadal. Thanks, Peijin. Great talk and very interesting work. Quick question. The 3D plot of Wavelength modeling for the theta angle, which magnetic field model is used? PFSS?
It's a CME model at Coronal. It's also developed by Predictive Science, but it's for sure not PFSS. It's a PFSS, as you know, it's just a potential field extrapolation. It's a static from a static surface and extrapolate the magnetic field. And the magnetic field model itself, it's a CME model, so have a simulation what the simulation can do is it can predict a time series of volume, and the volume contains temperature, density, magnetic field. The magnetic field, it has any coordinate. It's not any coordinate, but it's a coordinate grid, and you can just pick up at the surface where you want to have the magnetic field vector, and for that location you do the interpolation. You get a vector, and compare that vector with the volume surface. You will get a theta angle. That's how that angle is, but it's not from PFSS. Yeah, thank you.
If anyone has any more questions, please let us know. So while folks are thinking, can you just tell us what made you, maybe it was from when you were a little kid, what made you interested in the stars and doing this and the sun and this kind of work?
But yeah, to be honest, when I was a kid, I live in the city, and I don't have much chance of seeing a lot of stars. But once in a while, when I was in the more far away, like a hometown, urban area, and when I see the skies, it's really amazing. That's probably very inspiring. To get into this career, that's probably not due to the stars and the stuff. It's just to see the stuff that other people haven't seen. Is a really great feeling. It's not really like, okay, so this sky is cool, and I go to an area and see, okay, the sky, there's so many stars, and can see the Milky Way. It's just look at the things that have never been seen by anyone else in the world. It's feeling is great. So when I was at LOFAR, like 2 years ago, there was eclipse happening. And with Pietro Zucca, he was my supervisor at the time, and was coming. At that time, we were actually at a conference and during the eclipse and saying, okay, so there's an eclipse. Let's schedule observation to take some images. At that time, I did the data processing. I did all the calibration and plotting stuff, and so that will be the first solar eclipse radio image in like 40 or 50 megahertz that have never been processed, never been seen. And I got to be the first person to see that in the whole world. It's so this kind of feeling is great. So, and everyone else, what everyone else has been processed by me. It feels like a lot of responsibility, but this process is really fascinating as well. So that's what I really like to do observations, just because I can see things a lot further away and or beforehand.
Thank you so much. That's fascinating, and those are just really cool thoughts. Thank you for sharing.
Thank you.
It doesn't look like we have any more questions, so I'm going to turn it over to Cindy.
Yeah.
Thank you very much again, Peijin, for your fascinating talk. We hope everybody online had enjoyed it. And again, just want to say, please join us for our next seminar in a couple of weeks. And if any one of our science staff wants to give a talk, please let us know as well so that we can feature you as well. Thanks very much, everybody, and good afternoon.
Thank you.